Am I audible?
Yes, sir.
So this will start in 2 minutes. Okay, we have still time.
Excuse me, sir.
हेलो, हाँ बोलो।
सर ये पीपीटीज अपलोड कर दीजिएगा गूगल क्लासरूम पे।
हाँ मैं कर दूंगा, आज कर देता हूँ।
एंड सर बुक बता दीजिए कोर्स के लिए।
बुक भी मैं अपलोड कर दूंगा, ठीक है ना। 2-3 बुक्स जो है रेफरेंस आप किसी से भी देख सकते हैं, क्योंकि मैं डिफरेंट बुक से पढ़ा रहा हूँ, ठीक है ना। तो मैं सारी बुक आपको कर दूंगा, जिससे मैं पढ़ा रहा हूँ वो भी बता दूंगा मैं।
सर प्लीज आज कर दीजिएगा, कल क्विज है तो।
ठीक। Okay. So present. Fine. So in the last class we have seen the arithmetic instructions, right? So how addition, subtraction, multiplication, and division, right? So this were the basic instructions that were there in our 8086, right? So the next part now we are moving towards is the logical instruction. Okay, so we have seen now till now two type of instruction. First was your data movement instruction like move, fine. So then we have seen the arithmetic instructions, and now this is the third part, fine. So this is again the one of the most important instruction set we have. Okay, so rest of the remaining instruction set is kind of a, you can say, are less used in our 8086. So, right, so this is why there is something known as a 90-10 rule in a programming, right? So because you're all computer science students, so I guess either you know or know this rule, 90-10 rule. Okay, so this rule basically is not a particular rule, it is kind of a philosophical statement, right? It's not always valid, but most of the time it's valid. It's 90-10 rule, but it says that if you write any program, okay, so using some instructions, then 90% of your program will take only 10% of the instruction set, right? So let us suppose you have 100 different instructions in your instruction set. Okay, so the 90% of your program will only have 10 instructions only, right? And the 10% of your program will have something from the 90% of your instruction, right? So the 90 instructions will be used only 10% of the time, and for the 90% of the time only 10% of the instructions are used, right? And why it's so? Because in a microprocessor, that the basic aim of your microprocessor is to do some arithmetic and logical operation, right? The rest of the instructions are just, it's kind of a handful, just to make the help of your arithmetic and logical operations, right? But the ultimate aim of your microprocessor is to do some calculations, fine. So that's why it's known as a 90-10 rule. So that 90% of the time you're just using a 10% of the instruction, right? So that are basically your arithmetic and logical instruction, right? So your main, but it's not that you don't need other instructions, you do need, but for the less time, right? That's the thing. So now we are moving towards the logical instructions. So you know that what are the different logics uh, you have in your digital electronics. So and or not XOR type of things, right? So what our 8086 can do, right? So we will see. So precisely in our 8086 we do have instruction for AND operation, or exclusive, or and not, fine. Rest of the uh, operations like NAND and NOR, that is not there. Okay, so although we can do, but we don't have any specific instruction for doing them directly. Fine. So what we have AND, or XOR, and NOT. Fine. We also have one more instruction which will perform some logical type of operations, that is a test instruction. Okay, so it is very much comparable to your CMP, right? So that we have in our arithmetic instruction, that we have a compare type of instruction, fine. So similarly we have a test instruction, so that will behave very similar to compare, so that we will see, fine. But for the timing you have to remember that our AND, or XOR, and NOT are the four basic logics that can be performed directly by your 8086, fine. And we also have one test instruction, fine. So first of all we start with the AND. Okay, so I need not to tell about how the AND gate works, fine, or the AND logic. So you know that whenever the both one will there, then you get a one, fine. Rest of the time you will output will be zero, fine. So the basic syntax of your AND instruction will be something like this: AND destination and source, fine. So simply by putting AND, it is uh, understood that you are doing a AND operation using. Now again, you can have a two registers with you, fine. You can have a one register and one immediate value with you, fine. So your data can come either from the register and from the memory, fine. So both of the data can come from the register, okay. But both your data can't be given directly. Like, so if you say and 08 and 04, okay, so it make no sense, fine. So because you are putting both the values immediately, so although then where it will store the data, right? So after ending, which register will get the data, it is not there, so it is wrong. Okay, so you have to give at least in your destination there you have some register with you, fine. So let us suppose now you're doing AL04, so it is fine, right? So whatever is the content of AL, that will be end with your 04, and the content of your ending will store in your AL register, fine. Because after result you need some memory where you want to store, right? So that will come from your destination part, fine. So your destination has to be either a memory or a register, fine. Your source can be any immediate value or a register or a memory, fine. So these are the basic things that you keep in mind while programming an operation, okay. And although you know that you're using your logical instructions, your carry flag will also changes, right? But for ending operations you have to keep in mind what are the changes that we have in our flag register. So your carry flag and your overflow flag, it becomes zero after end, okay. So that is kind of a fixed, right? So you need not to see the actual value, okay. So the carry flag and the overflow flag will get a zero after end. Your auxiliary flag is kind of undefined, fine. So again, the undefined means series is a don't care condition. So after ending, you will not take care of the auxiliary flag content, fine. It is kind of undefined. So what happens also, or what precisely affect your end operation? Your parity flag, your sign flag, and zero flag is basically the flags that are affected and that are meaningful to any programmer, fine. So again, you have to remember the two things. If you are doing any arithmetic and logical operations, you have to keep in mind what is the content of your output and the content of your flag register, right? So collectively your microprocessor will decide the output, fine. So output register content, For the timing, it is AL here, okay, and your flag register content, okay. So there are some example here, okay. So let us suppose first example is AND BL AL. So it's simple. So it will just AND your AL content and BL content. So let us suppose the AL content is 93 hexa and BL content is 75 hexa. So it will AND your bit by bit, it will AND, okay. So 1 and 1 will give you 1, 1 and 0 will give you 0, 0 1 will give you 0 again, okay. So it will do the ANDing bit by bit, and whatever the content will be there at the after the operation of AND, that will be stored in your BL register because it is your destination register, fine. So that's how you can do ANDing of two 8-bit numbers, fine. You can also do a 16-bit ANDing, fine. So this is the second example. So here you are, yes,
सर वो फ्लैग वाला दोबारा बता दीजिए, फ्लैग
फ्लैग
बिट्स
वाला बता
वाला।
रहा हूँ मैं। फ्लैग वाला फिर से रिपीट कर देता हूँ मैं। फ्लैग में आपको क्या ध्यान रखना है एंड गेट में, कि एंड गेट में आपके कौन से रजिस्टर आपके अफेक्ट होएंगे। ऑलवेज रिमेंबर योर पेरिटी फ्लैग, साइन फ्लैग एंड जीरो फ्लैग, these three flags are going to be affected, or it is kind of a meaningful to you, fine. Carry flag and auxiliary flags becomes zero after ending, okay. So these are both zero after ending, and the auxiliary flag is kind of undefined, okay. So it is kind of a don't care condition. It can have a value of 0, it can have a value of 1, but okay, so it's kind of undefined to you, okay. So the meaningful flags after ending for you is only parity flag, sign and zero flag, fine.
ओके सर।
So now I was discussing the 16-bit ending. Okay, so if you can do 16-bit ending, so you have to give a 16-bit data. Okay, so here this example that one of the content will be stored in the register CX. Okay, and one of the data you are giving in the instruction only. Okay, so that's how you can do the ending of two 16-bit number, and again the data will be stored in the CX register. Fine. Now there is a term known as masking in our 8 microprocessor. Fine. So whatever, so this will be used when we discuss the interrupt. Okay. So the interrupt we will see what we will use that term. But what that basically meaning is, so masking basically means uh, when you want to clear some bits, or clearing basically means you want to make zero, okay. So whatever the contents of that memory location is, you want to make them clear, okay. So that particular process is known as masking in our microprocessor, fine. So for masking you need a AND operation basically, okay. So the AND operation basically clears the bit of a binary number, okay. So how it will do, you can see this particular example. So let's see you have some number here, okay. So these are the don't care conditions there. So let us suppose you have some numbers, it's a 8-bit, let us suppose it is a uh, data which is stored in particular memory location, okay. And it is required in your program, or it's your requirement that you want the last 4 digits or the LSB, okay. The last digit, that means this thing, you want to make it zero, right? So you don't want to make your higher digit to be affected, you just want to make your lower digit to be zero, fine. So you simply put this number in one input of and you will put a series of number, that is 1111 and 0000 to the second input of your AND, right? So you can see clearly that whatever be the content here, if you do a ending with 0, you will get a 0, fine. So it is very simple logic. Then if you do a ending with 0, you will get a 0, right? But if you will end with 1, then your bits will not be will not be affected, fine. So if it is 0 here, so 0 1 will give you 0. If it is 1 here, you will get 1, right? So you will get the same thing at the output that is there in the before, fine. So it is only affecting your lower digit, it is not affecting your higher digit, fine. So that's how you can mask your number, okay. Or masking again means you can clear your number, okay. Or clearing again means if you want to selectively make 0 to some bits, okay. So that selective uh, clearing of your bits is known as masking, okay. So you give the pattern something like this upon your requirement, fine. So masking can be done using AND operation, fine. So this is the main work of your AND, fine, to do the masking. Is it clear to all of you? Any query?
यस सर, क्लियर।
So next we are moving to the OR gate, okay. So I again need not to tell about what a NOR or gate do. Fine. So the basic syntax may same, no change. Okay, and no change about the your flag register also the same thing. Only difference is that it will do the OR operation, right? Rest of the conditions are as similar as your AND instruction. Fine. So I'm not giving much time to it. You can always see this thing. So very similar to that. But then again, why we use a OR gate? Okay, so if you want to make some digits one, right? So masking means something, making something zero, and it's can you can say it as a unmasking. Okay, so it will just opposite of your AND gate. So first of all, we see the example. Okay, so this is your OR BL. Okay, so this is the syntax of your OR instruction. Okay, so again, it will OR your BL content and AL content and store the data in your BL. Okay, and similarly, you can do a 16-bit of OR operation, right? Now let us see this example now. Okay, so let us suppose you want some bits to be set, right? To set basically means you want to make that bit one. Fine. So that can be done again by OR gate, right? So the masking will be done by AND gate and the unmasking will be done by OR gate. Fine. So let us suppose again you have some random number here and you will put in a one input of your OR gate and you will put one input of OR gate something like this. So you can see here whatever be the content of your higher digit, that becomes one here, fine, because you are now ORing and it is not affecting your lower bits, fine. So again, depending upon your requirement, I'm telling you, okay, you can set your bits selectively. Okay, so if you let us suppose you want to make the, you can say this digit and this digit to be one. Okay, so what will be your pattern? So you will give a pattern of something like this: 0 1 0 0 0 0 1 0. Okay, so you give this pattern to this input. Okay, so if you do this thing, you will get one in that particular locations. Fine. So that's how you can manipulate your bits. Fine. So either you can set or reset selectively by using AND and OR gate. Fine. The rest of the operation, you know what your AND and OR will do. Okay. But these are the two things that are, basically used in our programming. Okay. Fine. So next instruction that we have the XOR. Okay. So the syntax is very simple. XOR, destination, and source. Fine. So again, you know the logic of XOR. It is A bar B plus AB bar. Okay. So basically, it will give the output when you have some dissimilar types of inputs, right? So it will give no output when you have a similar kind of inputs. If you have dissimilar or different inputs, then it will give the output. Fine. So that's how your XOR can be concluded. Any other about the parity, whether it will a even parity checker or a odd parity checker, your XOR. Okay, so you can see here just by looking into the truth table, you can say that whenever you have a even number of ones, you will getting a zero here, and whenever you have an odd number of ones, you will getting a high output. Fine. So it is also used for parity checker. Fine. So again, the flag register condition again remain the same. Okay, nothing new in XOR also. Fine. So then when our XOR is basically used, fine. So you can see again with this example, when you want to selectively want to invert some bits, fine. So if you do simple a NOT gate, okay, so that will completely invert your bits, 8 bits or 16-bit data. But if you want to selectively invert some bits, then you can use a XOR gate. Fine. So that's how you can see the example here. Let us suppose you have some random number again here, and you give a input of something like this to XOR, right? So what it will do, you know that. Let's take example here. I'm taking 0110 here. Fine. So in the input you have 0, you XOR it with 1. So you what you're getting to get? You're getting 1 here. Fine. So you will get 1 here. When you do XOR of 1 and 1, you will get 0, right? So when you do XOR of 1 and 1, you get 0. When you get XOR of 0 and 1, again you get 1, right? So basically you are complementing your number. Fine. So but if you give 0 to the XOR, so your data will remain unchanged. Let's see. Let us suppose you have number 1001 here. So if you do 10, you get a 1. If you do 00 of XOR, you get 0, 00 again 0, 10 again 1. So these are kind of a unaffected. Fine. So whenever you give 0 to the XOR, your bits will remain unchanged. But whenever you give 1 to your XOR, your bits will simply get complicated. So not complemented. Fine. So that's how, if you want to do again selectively inversion of your bits, fine. So there you will can use your XOR. Fine. Any doubt? So your AND or an XOR are basically used for doing some selective kind of operations in a particular data. Fine. Next, what we have is a NOT instruction. So the syntax is very simple. You have only destination here. Fine. So you have, because you have just one operand, you're just doing the NOT. That means you're just doing the complement of your data. Fine. So the syntax is very simple, and no flag register is going to be affected here. Fine, because there is a no two operands are there, just one operand. Fine. So your flag registers has some change when you have two operands. Fine. So the basic syntax note AL. Okay, so if let us suppose the content of AL was this thing, after doing note, you will simply get the complement of this. Okay, you can also do a 16-bit note operation. Okay, so the format is something like this. Okay, so it is one of the simplest instruction that you can have. Okay, simple note. Fine. So next we are moving towards is our test instruction. Okay, so what basically test instruction do? So whenever you write a test, basically it will perform a AND operation. Okay, it's nothing uh, new. Okay, so you know what is the AND operation do. But again, then what is the difference between AND and test? So the difference is very similar that we have discussed with compare and subtract. Okay, so the same difference will come here, that your test will just do the ending and it will just change the flag register values. It will not change the values of your registers itself. Okay, so it will just check the and it will just check do the ending, but it will not affect your actual data. Fine. So the same concept that we have seen in the compare and subtract part. Fine. So your register content will not change, your flag register will change here. And which flags will change here? So your parity flag, sign flag, and zero flag will be updated after your ending. Fine. So we will just take an example here. So let us suppose you are given a test ALCL. Fine. So it will test, or it will do the ending of your AL content and CL content and just update the flag register. Okay, but it will not change anything in the AL and CL. Fine. So again, the format is something like this: test ALCL. It will do a 8-bit comparison, and test BXCX basically do a ending of 16-bit. Fine. So that's how your test instruction basically behave. Fine.
एक्चुअली में सर,
So yes.
देन सर इसका चेंज क्या होगा, क्योंकि ये तो सिर्फ फ्लैग्स को इफेक्ट करेगा, एक्चुअल नंबर को तो करेगा ही नहीं।
हाँ वही तो
देन
यहाँ
इसका
बस फ्लैग की चेंज। हाँ तो आप एग्जाम्पल ले लेते हैं ना, आप चेंज हो जाएगा ना आपको फ्लैग रजिस्टर। मान लो आपका डाटा था, एग्जाम्पल ले लेते हैं, आपने से पूछा मैंने ये एक नंबर मेरा एल में ये था, ठीक है, सीएल में ये था 011, कोई भी ले लो, रैंडम नंबर कुछ भी ले लो मैंने, ठीक है ना। तो आपको अब ये देखना है कि एंड के बाद जो मेरा नंबर आया वो पेरेंट, आपको बस ये चेक करना था, आपको ये नहीं मतलब था कि एंड के बाद क्या डाटा है, आपको बस ये चेक करना था कि एंड करने के बाद क्या मेरा नंबर में इवन नंबर ऑफ वंस आ रहे हैं या और नंबर ऑफ वंस आ रहे हैं, ये आपकी रिक्वायरमेंट थी। ठीक है, तो आपने फर्स्ट एंड किया, तो 1 1 का एंड 1 0 0 0 0 0 0 0, राइट। सो यू आर गेटिंग जस्ट 1 हियर। ओके, सो इसका मतलब आपके पास यहाँ पे और नंबर ऑफ वंस है, तो इसका मतलब आपका पेरिटी फ्लैग कितना हो जाएगा यहाँ पे 0। बस आपका अब आपका पेरिटी फ्लैग अपडेट हो गया 0 से। ठीक है, बस आपने बस इतना चेक करना था, क्योंकि आपको कि एंडिंग के बाद जो मेरा रिजल्ट आ रहा है उसके अंदर कितने नंबर ऑफ वंस है, इवन नंबर ऑफ वंस है या और नंबर ऑफ वंस है, वो आपने टेस्ट किया। आपने टेस्ट के बाद उसने एंड किया और फ्लैग रजिस्टर को चेंज कर दिया, पेरिटी फ्लैग को 0 कर दिया, यानी कि आपको पता चल गया कि आपके पास और नंबर ऑफ वंस है। ठीक है ना। सिमिलरली अगर आप चाहते हो कि एंड के बाद क्या मेरा आंसर 0 आ रहा है या नहीं आ रहा, ठीक है ना, तो आपको बस सपोज यहाँ पे ये भी 0 होता, ठीक है ना, तो ये 0 आ जाता है यहाँ पे, तो आपका 0 फ्लैग अपडेट हो जाता है 1 से, कि आपका मतलब कि एंड करने के बाद जो आपका आउटपुट आएगा वो 0 आ रहा है, ठीक है ना। तो ना आपने AL में कुछ चेंज किया, ना आपने CL में कुछ चेंज किया, बस आपने बस चेक किया कि एंड करने के बाद क्या सिचुएशन हो रही है, ठीक है ना, क्या आंसर मेरा 0 आ रहा है कि नहीं, क्या नंबर ऑफ वंस कितने आ रहे हैं, ठीक है ना, तो वो टेस्ट करेगा। फाइन
सर ये जो इंस्ट्रक्शन लिखे हुए हैं सर, ये 8086 के हैं।
8086 के, हाँ।
यस।
आपको क्या लगा 8085 के?
नहीं सर, 8085 में तो सर AL और CL का पेयर बनेगा ही नहीं, क्योंकि A
हाँ
के साथ पेयर नहीं
हाँ
बनेगा।
बिल्कुल बिल्कुल, सब उसमें अलग है ना, उसमें तो AL कुछ मतलब ही नहीं होता, BX कुछ मतलब नहीं होता है ना, वो 8 बिट का होता है, हम तो A और C लिखते हैं बस। और कोई डाउट? ठीक है, टेस्ट और एंड में कंपैरिजन आता है बेसिकली यही, ठीक है, कि क्या डिफरेंस है टेस्ट में और एंड में, तो आपको बस ये बताना है। क्लियर? So let's go now. So basically it is written here, so basically we will use the test when we do the jump instructions. Okay, so because you know that in the jump instruction, we have discussed in the lab also, your jump instruction basically see your flag register values. Okay, so it does not care about what you have in the accumulator, it will just see what you have in the flag register. So then it will decide whether it want to jump to a particular location or not. Fine. So there your test instruction is basically again helpful. Fine. So whether you want to jump or not, that will be decided by your zero flag register, and that can be checked by your test instruction. Fine. So here your example is given here. So let us suppose you have some, again, a random number, and you want to just check whether this number is 0 or not. Okay, so you just put a 1 here. Okay, so you just put 1 here. If you get a 1 here at the output, that means you have 1 here. If you just want to check only 1 bit, okay, so you don't care about the rest of the bit, you just want to check whether this number that is here, this number, either it is 0 or it is 1. Okay, so you simply do a test thing, you will put a 1 here. Okay, so it will just do the AND. Okay, so if 0 and 1 is 0, okay, so if you get a 0 here, then your 0 flag will get high. Okay, because you are getting a 0, so that means you have now checked that your this bit is 0. Okay, so that's how you can check whether a digit is 0 or not there. Okay, at that particular bit, is it 0 or not? Okay, just by doing it testing. And if it is 1 here, then 1 ending 1 is 1, that means now you get a 1 here, that means your 0 flag will becomes 0. Okay, so if your 0 flag is 0, that means you have some number there. Okay, so you're not getting a 0, that means it is not a 0 there. Fine, so that's how you can check a bit whether it is 1 or 0 by simply doing a testing or test operation. Fine, and again you can test any number, any position of bit. Okay, either you can do this bit, you can check any of the bit. Fine, so that will be helpful when you want to check some conditions. Fine, so that was your test. Now the next instructions that we have is shift and rotate type of instruction. Okay, so in the shift basically we have 4 different instructions. Okay, so we will see it one by one. Okay, but what are the 4 instructions basically are? So first is your SHL. Okay, so SHL basically stand for your shift logical left. Okay, SHR is basically shift logical right. Then we have a SAL. SAL basically stand for shift arithmetic left, and we have SAR, which is shift arithmetic right. Okay, so we'll see this one by one, don't worry about this, but for the timing you have to just remember the acronyms. Okay, so what they all stand for. Fine, so how they will operate, so that we will see. But why you are using this thing, see, we will see that once you shift your data in a left or a right thing, you are basically doing multiplying or a divide. Fine, so how this thing is happening, you can simply take one example, right? Because you know that our binary, this 101 is nothing but 0248, right? So that's how you can calculate this number. So this is nothing but 9, right? So that's how you calculate this number is 9. So if you shift this thing here, this one here, okay, so then what will happen? Then your new number will be 1010, right? So that's been, now you are basically multiplying it with 2, right? So when you are shifting your data in left thing, you will see that you are multiplying your content with 2. Okay, so if you shift 2 times, then you know this one will come here. That means now you're getting 1101, right? So that's why now you're getting a 4. You're now multiplying with 4. Okay, so this thing is very much clear when you do the experiment. Okay, so in the experiment part, we will see that by doing a one left shift, you can have a multiplication of 2, right? So the people who has done the lab in the last class, they know, right? So we have different type of a shifting operations. See, so that we will see now one by one. So first of all, we have SAL and SHL. Okay, so both are kind of the same. Okay, so they both will do the same kind of operation. Okay, so both are going to shift your bits in the left direction. Okay, so AL basically means arithmetic kind of your operations, and H basically means your logical. Okay, so whenever you see H, that means you are doing a logical operations, and whenever you see A, that means you are doing a arithmetic operation. Okay, so what is the difference between then arithmetic and your logical shifts, right? So the logical shift operations are basically used for your unsigned numbers, and your arithmetic shifts are basically used for your signed numbers, right? So it is very similar to that what we have done in multiplication, MUL and IMUL, right? So although both will do the multiplication, but one is more dedicated towards your signed numbers and one is more dedicated for your unsigned, right? So similarly, if you have signed numbers, then we are going to use arithmetic shifts, and if you are using unsigned numbers, then we are going to use logical shifts, right? So as the name suggests, we are going to shift our contents of some register in a left direction. Okay, so what is the then the algorithm for this? Okay, so SA and SH are the two mnemonics. Okay, so then again you have a syntax of destination and count. Okay, so count basically tells you how many times you want to shift. Okay, so if it is not there, then the default value is 1. Fine. So if you don't write anything here, that means you just want to shift 1 times. Okay, but if you write something, some number 2 3 4 5, that means that many number of times you want to shift your data. Okay, then what is the algorithm here? So that should remember that this instruction basically shift each bit in a specified destination to the left, and 0 is stored at the LSB. Okay, so and the MSB is shifted into the carry flag. So two things are happening here, that whatever the content of your MSB, that will be go to the carry flag. So you can see here my content of MSB is 1 here, that will go to the carry flag. Okay, so that you can see here. Okay, so one thing that will happen. Okay, so your MSB, always remember, will go to the carry flag register. Fine. Your LSB, whatever the content of your carry, okay, so it will be always becomes 0. Okay, so in the output you have to put LSB as 0. Okay, the rest of the bits will go a left shift, right? So this one will now go here, this one will go here, this one. So you are shifting left. Okay, so this data is because you want to shift, this is going here. Okay, so that's why you can see simple thing, you're shifting your data in the left direction, but in your LSB you have to put a 0. Okay, so it is mandatory. Okay, so when you do something like this, it is known as a shifting in left direction, and it will be done by your SAL and SHL instruction. Okay, so both will perform same thing. Fine.
एक्सक्यूज मी सर।
हाँ बोलो।
सर जैसे आफ्टर एग्जीक्यूशन के बाद 1 आ गया कैरी फ्लैग में, अगर हम एक बार और करेंगे तो 0 आ जाएगा, उसमें 1 तो लॉस्ट हो जाएगा जो
हाँ
उसमें पहले।
नहीं, वो लॉस्ट हो जाएगा, वो 1 लॉस्ट है ना। तो आप नहीं देखा आपने कि यहाँ पे आपको ये आप देख रहे हो अभी कि शिफ्ट जब आप करते हो तो आपका जो कैरी फ्लैग का जो भी कंटेंट है वो लॉस हो जाता है ना। ये चीज अभी हम देखेंगे जब रोटेट करेंगे तो नहीं होगा वो। तो रोटेट में हमारा कैरी फ्लैग भी कम पिक्चर में आएगा, पर अभी हमारा क्योंकि हम जो हमारा प्रिसाइसली हम जो शिफ्ट कर रहे हैं, हमारा जो मेन एम है वो रजिस्टर के कंटेंट को शिफ्ट करना है, ठीक है ना। रजिस्टर के कंटेंट को शिफ्ट करना है, ठीक है। तो फिर से आपका जो दिस थिंग रजिस्टर कैन बी अगेन either of 8 bits or a 16 bit, okay, depending upon the instruction. Okay, so you can do a 16-bit shift also, and you can do a 8-bit shifting also, fine. And also how many number of times you want to shift, that will be decided by your count register content. Okay, so I have told you in the last class, fine, that your CX register is sometimes used for counter, fine. So whatever be the content of your CL register, that will decide how many times you want to shift, fine. So we will see the now the example here, that will be, then you can be clearly understand. Okay, so if you write SALCX1, okay, so that means you just want to shift the content of your CX register by just one, fine. So it is as simple as that, fine. So you're just shifting your content of CX register only once, fine. Now the next instruction is basically collectively this two, okay, so it's not two different instructions, this is actually one. You have to interpret it is kind of a one thing. Okay, so what you are doing here, firstly you are moving 5 value to the CL. Okay, so basically now you are making your counter value 5. Okay, that means you want to shift 5 times. Okay, so that's why you put a 5 here, right? Again, depending upon your program, how many times you want to shift. Firstly, you have to store that value in your CL register, right? So let us suppose you want to rotate your CL your any register content by 10 times, then put 10 there. Okay, so move CL 10 hexa. Okay, so 10 there again, that more sense A, right? So 0A. Okay, then it will shift 10 times. Fine. So firstly you have loaded your counter, and then you put SAL AXCL, right? So that means basically you want to now shift the content of your AX register how many times? 5 times. Okay, so you need not to give the value directly. Okay, so you can also use your CL register, right? So whatever the content of your CL register, fine. So that thing again we have seen in the programming, that after doing this we do a decrement of CL, right? So after one shifting, then your CL will simply get decrement by 1. Okay, so internally it will then decrement by 1, then its value get updated to 4 3 2 1 0. Okay, so that's how 5 times you will get the rotation or shifting, fine. So that is the syntax of your if you want to shift your register content in the left direction, fine. So next we have is SHR. Okay, so please it's not as same as the SHL. Okay, it's not just opposite of that, so people make a lot of mistake here, fine. So please see this carefully. So although it is just opposite of that, see now you can see this figure, right? So what I have now done is very can say smartly, I have put my carry flag, which was before it was there, right, in the last example, but now I have very smartly put my carry flag there, fine, in this location, because as I told you, our main aim is to shift the content of register, right? So carry flag is just a kind of a what you can say is a kind of collector of your extra bit, fine. So that's why we have now used a carry flag register position here. Okay, so what it will do, so basically this instruction shift each bit of your destination or your register content to the right, and 0 is stored at the MSB position, right? So MSB will now get the 0 data, fine, and your LSB is going to shift in your carry flag. Okay, so I'm again repeating and I'm again kind of comparing our SHL. Okay, so in the SHL, what was happening? My MSB bit was going to the carry, right? And my LSB was updated to 0, right? But here, my LSB will go to the carry register, and my MSB will update it to the 0, right? Just opposite of that, right? So let's see the example here. You can see here. So that was my number before shifting. Okay, so as I have to now shift the LSB to the carry flag, so now this one will go here. Rest of the bits will now take the position, or it will shift right. Okay, so this 0 will come here, this will come here, this one come here, this 0 come here, one will here, this 0 here, this here. So this LSB will now can become vacant. Okay, so that you have to put a 0 there. Okay, sorry, MSB. Okay, so MSB will get a 0. Okay, because it will get vacant because you are shifting right. So all the bits are going in this direction. Now this site is vacant, so that's why you put a 0 here. Fine. So that's how you get a SHR. Fine. Any doubt in this thing? So you have to remember this thing. Fine. So what you are shifting. Again, you can do the same thing, 8-bit shifting or a 16-bit, and if how many times you want to shift, that can be taken care by your counter register. Fine. The rest of the things are very much same. So the example is same, right? So SHR CX1 basically means you want to just shift right one times. Fine. But if you want to shift some post 5 times, then you have to put first 5 in the CL. Then you can go SHR AXCL. Right? So next we have now SAR. Okay, so SAR basically stand for shifting right, but using some arithmetic numbers. Okay, arithmetic basically means you are going to use some sign numbers. Okay, so SAR will now get differs. Okay, why it is not differ? Because you are using now sign numbers. Okay, so in the sign number you know that the MSB contains the information of your sign, whether you are using a 0 or your positive number or a negative number. Okay, if it is 1, that means you know that you are using a negative number, right? So your MSB is kind of a reserve for getting the information of whether you're using a positive number or a negative number, right? So that's why what we will do here. So this instruction basically shift each bit in the right direction. Okay, but now there is a catch here. Your MSB position will not change. Okay, so whatever the content of your MSB, that will not change. Okay, so it will be simply copied again. Okay, so your old MSB will be copied again to your new MSB position, right? So in the last case we are putting 0 there. Okay, but here whatever with the MSB, that will not get changed. Okay, so there is only difference there. So let's see again with the example. It's better understood by the example. So let us suppose we have a number like this before this. Okay, so you can see here my MSB is 1 here. Okay, my MSB is 1 here. So what you will do, first you will simply do the shifting right. Okay, so this 1 will go to the carry flag register, this 0 will come here, this will do come here, this 1 come here, this come here, this thing here, this thing here, and this MSB will no doubt will go to this thing. Okay, to this location, but the same content of my MSB will again copy here. Okay, so you can say that you are copying 2 times. Okay, so your new this data value, let's suppose this your location number 1 0, or this is 1. Okay, so both 0 and 1 position will get the same value which is stored in the MSB previously. Fine, so you are copying 2 times. One time you are copying to the first position, and also you are not changing the value at the MSB also, right? Why are you using this thing? Because you know that if we change this 1 to 0 in the sign number, then the whole number get changed, right? So you change from negative to positive, right? So that's why we don't want to change this bit here, because we want to keep that information safe, right? So that's how your SAR will perform. Any doubt in this thing, you may ask? Am I audible? Am I audible to all of you?
Yes, sir.
Okay. So please remember the difference between SAR and SHR. In SHR, I'm again repeating. In SHR, your LSB data will copy to the carry data, or sorry, carry bit. Okay, rest of the bits will be shifted to the right, and MSB will get a 0. Fine. But in SAR, your MSB will get the same value that was before. Rest of the data will shift to the right. Fine. So that's how your SAR instruction performs. Fine. So this was the shifting operations. Okay, so I guess we have 5 minutes. Okay, so let's see just one example. Okay, so similarly, we have a rotation instruction also. Okay, so a rotation instruction, so that the is kind of a loop. Okay, so shifting is kind of a it's a linear thing, and rotation is something kind of a circular thing. Fine, so that you have to make a loop. Okay, so in the loop, basically now your carry flag register content will also come into picture, right? So again, depending upon what type of rotation you are doing. Okay, so you can shift your data. You are again shifting your data from one location to another. Okay, but now you are doing so in some particular loop kind of a phenomenon. Okay, so in the rotation instructions, we can rotate either left side or right side. Okay, so we have again 4 different types of rotations in our 8086. Your RCL, that stand for rotate left through carry. Okay, so that through carry means you have to take care of your carry bit also. Okay, if you are doing ROL, so ROL simply means you want to just rotate the content of your register to the left. Okay, so you don't want to take carry flag with you. Okay, so that's the only difference between your RCL and ROL. That in the RCL, your carry flag will also take part in the rotation, but in the ROL, your carry flag will not take part. Okay, similarly, we have RCR and ROR. Okay, so RCR again stand for rotate right through carry, and ROR basically simple rotate right. Okay. So how this will work? So we just take today's one example, then we will stop. Okay, so we'll just take RCL. So what RCL do? So the basic syntax will remain this thing: RCL destination and count. Okay, so this instruction basically rotate all the bits in your register to the left side with carry flag also. Okay, so how it will rotate? So your MSB will be now placed in your carry flag register. Okay, and the previous value of your carry, that will be go to the LSB, right? So this is kind of a complete loop. It's very simple, right? So you can be again can understand by this particular example. So I'm taking the example here. Let us suppose the content of your carry flag register was 0, and this is the content of your register, right? Now if you do a RCL, what will be happen? So this MSB will simply now copy to carry flag. This 0 will go to the LSB here. Okay, and the rest of the bits will simply get left shift. Okay, so this one will come here, this 0 come here, this one come here, this thing here. Right, so you're making a complete loop, right? So the carry flag register also coming into picture. That means you are now using the content of your carry flag, right? So whatever the content of your carry flag, that will be simply copied to your LSB, right? So then when we are doing SAL, we are putting this LSB as 0, right? So we are not taking the carry flag register in our shifting, right? So the difference between, you can see here in rotation and shifting here in RCL, that your carry flag is also coming into picture. Fine. So that is RCL. So again, you can do 16-bit and 8 bits of rotation. And how many times you want to rotate, that can again given by your CL register. Fine. So that's how your RCL instructions looks like. RCL CX. Okay, so it will rotate the data of your register with your carry 1 times. Fine. So I guess it is enough for today. Okay, so try to learn all these instructions. Okay, so I'm just repeating what we had done today. I guess we started with the AND operations. So AND basically used for masking or for unmasking, not for selective XOR, for selectively inverting the bits. Not was just for inversion of your bits. Okay, then the test bit was again to check the contents of your ending result. Okay, then we have seen the shift registers. Okay, so this is again commonly used. Okay, so the four shifting that we have. Okay, SHL, SAL, SHR, and SAR. So again, when you do the left shift, your both A and H are kind of the same. But if you do the right shift, then because you're right shifting, then you're changing the content of MSP. So it will differ. So the SHR you have to keep in mind that your MSP is going to get value 0. Okay, but if you're doing a SAR, then your MSP will not change. Okay, so it will simply remain unaffected. So that was a major difference. Then we are now continue our this thing. Okay, rotation thing. So RCL and we had discussed today. Okay, so in the next class we will continue with this ROL. Right? Next class also we have a quiz lineup. So that's how we can also complete this part and with quiz. Okay, any query?
No, sir.
Okay, then. Thank you all.
Thank you, sir.